All right, David Gish here, professor at DMAC, just going to give you a little overview of Chapter 6, go through real quick some basics. We're going to look at a simulation as well to help describe something that's happening in this chapter. But we want to focus on the normal distribution in this chapter and some of the things it can do for us. So normal distribution, it's a continuous probability distribution for x. So in Chapter 5, we did discrete random variables. This is if you have a continuous random variable. And we know that as the normal curve, the bell curve. It's symmetric, right? Right down the middle is the mean, median, and mode. And it's on both sides. Nice and symmetric mirror image, right? Now, the big thing is what we do is lots of things have a normal distribution quality to them. So in other words, roughly symmetric. But if you're dealing, let's say, with data that's in miles and you're measuring something in miles, and maybe I'm doing something and I'm weighing it and I'm measuring it in grams, but then somebody else is collecting data about the, milliliters of some liquid. So we're all using different units. They're different, just measuring different things. They're completely unrelated, but they're all normal distributions, let's say. Well, it'd be nice if we could somehow speak the same language. And that's essentially what this idea is here. So if we use z-scores, you can convert any set of data that's normal using z-scores, and then you stack all the z-scores together and they fit on what is known as the standard normal distribution. So this is sort of like the universal language of normal distributions. We can all speak this distribution, all use this distribution, and it works. Visually speaking, the idea is, and by the way, the area under the curve of the normal distribution, we think of this thing as having an area of 1, or a probability of 100%. That all just kind of works and plays together, sort of similar to how the area is relevant in Chapter 5, if you caught that. So anyhow, standard z-score, that gets you to the standard normal distribution. All right, here we go. So here's kind of an animated image to show you what's happening. But basically, you take z-score, and no matter what your normal distribution looks like, it's kind of like thinking in Photoshop, right? You can stretch an image one way, the other way, or whatever. And so z-scores allow us to stretch and shape our normal distribution so it turns and fits into a standard normal distribution. So again, we've converted it to look like this now using z-scores, and then we can all use z-scores for whatever we want. So that's really helpful. One thing of note, so now when we use z-scores, we're going to use z-scores to help us with probabilities and all that fun stuff. Now, there is a table in your book. Now, your professors might disagree with this, and that is fine. It's kind of a preference in a way. But I would say do not use the tables. Don't use the tables. The tables are not very accurate. Well, I mean, they're accurate, but they're only accurate within what's in the table. So if you have anything not in the table, then you sort of have to guess in between and all this and that. They're just kind of a pain to use. But we have software that does this stuff now. So what's in this table can be spit out using software and can be spit out and done more accurately with software. So we should be using the software. So we should use StatCrunch. It's better, it's more accurate. So if the homework says use a table or whatever, at least from my perspective, do not use the table. Use StatCrunch. All right. So how do you use the table or the calculator in StatCrunch? So you go to StatCrunch, calculators, normal, and then it'll spit it up. And always leave this as 0 and 1, and then this box is your z-score. So you can put a number in this box, and then the arrows will shade whichever way the arrow is. So less than is to the left, and then it'll shade it in, and then it'll tell you what that is as a value. Okay? All right. So, and then you could do the other way. So flip it greater than, and then it could shade to the other direction. It'll spit that out for that z-score. You can also click between, and then you could put two different z-scores in, and then it'll shade in between, and it'll tell you that probability or area in between. So really fast and easy to use this calculator. All right. Now, the big thing in Chapter 6 is this thing called the Central Limit Theorem. So here is the idea behind the Central Limit Theorem. Imagine you had a huge population. Now imagine you could go out there and take a sample. Now instead of making a distribution of this sample, let's take the sample and find its mean. And then we'll throw it down here. Let's do that for another sample, throw its mean down here. Let's do that for another sample, another sample, another sample, another sample. And if we stacked all of those sample means together, they would make a new distribution. Well, what does that distribution look like? Is it symmetric? Is it skewed? What is that? And by the way, this is a distribution of sample means, so we call it a sampling distribution. Okay? So what the Central Limit Theorem tells us is that for any population with any distribution, the distribution of the sample means is approximately normal as the sample size increases. All right, so if I have a distribution that's not normal, so like this one is double peaked and all that, it could even be skewed. But if I take samples of 30 or larger, and then I take their sample means and I stack their sample means together, they will actually turn into a normal distribution. Likewise though, if I start with a normal distribution and I take a bunch of samples, the size doesn't matter. It doesn't have to be 30. If you start normal, you're going to get normal, and that's automatic. So let me show you this in a simulation real quick to hopefully explain this idea. Here's a simulation I have. And so this is a stat crunch, and so I have a very skewed right population here. This has thousands and thousands of values. It's a simulation because we don't have time to go out and do this in real life. But notice this population has a mean of 14 roughly and a standard deviation of 11. Okay, and then there's all the other values if we care, but we don't really care. All right. So let me take samples of size 5, right? So if I took one sample, so here it is, it's grabbing a bunch of things out of that population, 5 things. It took the mean, and then here it is, there's the mean down there, right? And then here's another sample of 5, and it's taking these values randomly, found the mean of those 5 values, stacked it down here. Now let's do 5 at a time. All right, and so there's 1, 2, there's another one, and so see, we're creating a sampling distribution down here. These are sample means, and then let's see what happens here. So now let's do 1,000 at a time, and another 1,000, and another 1,000, another 1,000, another 1,000. So I've taken 5,000 samples, right, of size 5. Now it kind of looks symmetric, but you can see it is a little bit more skewed to the right. But what's that Central Limit Theorem say? It said if it's not symmetric, then you should choose samples of size 30 or larger. So let's redo this with size 30. So if I do 1,000, 1,000, 1,000, 1,000, 1,000, 1,000, 1,000, right? There it is. Now this looks awfully symmetric, right? Looks awfully normal. And that's what the Central Limit Theorem says. Now you might be like, it's not perfectly normal. Well, we're also just past that barrier where we need to be at least that big, okay? Also notice some things. What's the mean of the population? 14.05. What's the mean of this entire distribution of sample means? So the mean of the sample means, it's 14.05. What about the standard deviation? Well, this thing was awfully spread out up here, 11.8. Notice this is a lot less spread. All right. Now let's check it out. So that's 2.1. Now let's redo this and let's choose sample of size 50. Right. So again, here's 50 randomly chosen things from the population. Take the mean, put it down here. Right. And then, so let's do that 1,000 more times, 2,000, 3,000. Okay. So again, this is a sampling distribution from this population. The means are roughly the same. Now, not quite, but awfully close. And now look, hey, remember the last one, it was a little bit wider. It's gotten a little more thin, right? So that standard deviation is not a perfect match. And in fact, I think I've seen a trend here. So if I bump this up to 100 and do this, look at that. So 14.03, not quite a perfect match, but I've only taken 8,000 samples. If I could theoretically take every single sample of size 100 out of this population, then these would be an exact match. But again, what's happening to that standard deviation? It's actually gotten smaller yet. And so that spread is getting smaller the larger my sample size. Okay, so notice that relationship. So if I went up to a sample of 1,000, check out, so it's going to get really thin. See, look how thin it is now, right? So the larger your sample size, the less spread out your sampling distribution is. But again, has roughly the same center. All right, now this was for a skewed population. Let me go back in here. Let me start with a bell-shaped one. So I start with normal, right? And now let me do those samples of size 5. So start out really small. Remember how when we did 5 before, it was skewed? Nope, no problem now. Start normal, it is normal, right? So I don't really need to worry about the sample size so much. If I start with a normal population, we're good to go. I don't need to worry about the sampling distribution being normal or not. Now, this has a spread of 2.2 when the sample is 5. If I bump it up to 50, check it out, it's less spread, right? So again, the larger the sample, the less spread out it is. All right, so that's what the central limit theorem tells us. So specifically, the mean of all the sample means should be the same as the original population mean, all right? And the variance is smaller. Well, how much smaller? Well, it's directly related to the size of your sample. So if your sample is larger, you're dividing by a larger number, which makes that variance smaller. And then likewise, your standard deviation is, when you take the square root of both sides, turns into this. So again, you're dividing by the square root of n. So the larger n is, the smaller the standard deviation of what though? The standard deviation of your sample means. Okay? Now this sigma sub x bar here, that is the standard deviation of the sample means, but we have a special name for that. We call that the standard error of the means. All right? So we'll refer to this as the standard error. So one last example then, and then we'll call it a day for the chapter and kind of our overview. So this is how this is powerful. So if we do this example here, this is about credit card debt. And by the way, this is adapted from actual data from Sallie Mae, one of the largest student loan lenders out there. So it says here, debts carried by undergraduate students are normally distributed with a mean of 3173 and a standard deviation of 1120. So on average, the average, let's see here, credit card debt is 3,173. Ouch. So question 1, what is the probability that a randomly selected undergraduate who is a credit card holder has a credit card balance of less than 2,700? So this is normal. I want to find some probabilities. Notice in the question too, what is the probability that a single one, a randomly selected undergraduate, a single one. So when I'm doing this, I need to think this exists on a distribution of single individual values. So that's just the original kind of distribution. So here's that distribution. 3173, and it's spread out with this spread of 1120, right? And so here's roughly 2700, that should be a 2700 there, not 25. I'm not sure what happened there. Well, I know what happened there. That's a mistype, but anyhow. So if you do z-scores, right, we will take this normal distribution, turn it into z-scores. That converts it into a standard normal distribution. And so that z-score, that mark there, has a z-score of negative 0.41. So if I go to StatCrunch and look that up to the left, that's going to spit out a probability of 0.3372. So what is the probability that an individual has a credit card debt less than $2,700? Well, it's 33.72%. Now, number two, let's say you randomly select 25 undergraduates who are credit card holders. What is the probability their mean credit card balance is less than $2,700? Well, this is a mean. A mean of what? A mean of these 25. So that's a sample. So a mean of a sample. So when I do this problem, I need to use a sampling distribution, because this isn't an individual value. Like back here, this was on the original distribution of individual values that had this center and this spread. But this is on a distribution that has sample means, on the distribution of all those sample means. But the Central Limit Theorem told us the mean of the sample means is the same as the population mean. So it still has this center, but it's not spread out like this. It's spread out like, it's not spread out by 1120. It's spread out by the standard error, which is sigma over square root of n. So that's 1120 over square root of 25. So when I do z-score, it's still the value, in this case, a value being x bar minus the mean, 3173. Now divided by your spread, but in this case, we're not spread by 1120. We're spread by the standard error, so 224. So that's how you calculate your z-score now. And so now my z-score is actually negative 2.112. And so if I look that up in StatCrunch and spit that out, that's 0.017. So what's this say? This says if I took 25 randomly selected undergraduates, the probability that their mean, the average of that sample of 25 is less than 2,700. That's really small, 1.7%. So that's like the size of a class. So the probability that the average credit card debt for an entire class is less than 2,700, not very big. All right. So that's kind of how you do this, and the uses of this. And this relies on the Central Limit Theorem, how we know that, hey, this is what happens when we look at sample means and stack all those sample means together. All right, so that's just two examples real quick. Lots more ways to kind of use and shape this, but hopefully that helps and gives you a little overview of what we're trying to accomplish in this chapter.